So welcome everybody to the software economics session at ICSI 2022. We have in this session 3 inspiring papers, and we are gonna start right away with the first one, which will be presented by Patricia Matsubara, and its title is "The Best Defense is a Good Defense: Adapting Negotiation Methods for Tackling Pressure over Software Project Estimates." So Patricia, please,
Okay,
your
thank you.
turn.
I'm sharing my screen. I hope you see it already.
Yep.
So, hi everyone. My name is Patricia Matsubara. I'm a PhD student at the Federal University of Amazonas. And today I'm presenting the paper, "The Best Defense is a Good Defense: Adapting Negotiation Methods for Tackling Pressure over Software Project Estimates." This paper was written with Professors Igor Steinmacher, Bruno Gadelha, and Diana Conte. And the context we have here is that in the software industry, we have people generating estimates for their tasks and software projects, and we also have people receiving those estimates. And these people work together to establish commitments, which define the set of features we're delivering and when we're doing that. And rationally speaking, we should base those commitments on the technical estimates provided by by estimators, because they're the people with the technical knowledge and experience to tell us how long a task will take, for instance. But when we look to other fields of knowledge, such as behavioral economics and psychology, they have results showing that humans are not necessarily rational all the time when they making decisions or acting in some situations. And the same happens when we're looking for this interaction of the generation of estimates and the establishment of commitments, because these things happens inside organizations which operate in a business market. They have, therefore, targets which are desirable business outcomes. And there are lots of people working together. They also have their own goals and their own agendas. And we have results in the software engineering literature showing that when these things interact, for instance, when estimates and targets collide, we have estimators suffering pressure to change their estimates. We also see that time pressure is pretty common in the software industry, and time pressure comes from unrealistic commitments. We also have industrial surveys showing that tight deadlines are connected to technical debt. And again, tight deadlines are about unrealistic commitments. So, in summary, the pressure over estimates impacts negatively the quality of the products we have. And in this context, we asked ourselves, how to empower software practitioners to resist pressure and defend their software estimates? And we looked for the literature about negotiation methods to get some help with that. But why negotiation? Well, let's take a look at a definition. A situation is considered to be a negotiation anytime that the involved people consider it to be a negotiation and prepare accordingly. They also are trying to gain something from the interaction. They need each other to get the results they want. They won't do it alone. They are communicating back and forth, and they are working towards an agreement. So we believe that the interaction of estimation and establishment of commitment has many of these characteristics. And we studied 3 negotiation methods to devise an artifact to support estimators when they are facing pressure over their estimates. And to understand more of our idea, I'll give you one example. Let's suppose people are making pressure over us for the delivery of a product on a tight deadline, because we saw that's problematic. And instead of simply yielding to pressure, acting as if, well, the other stakeholders are more powerful, there's nothing I can do about it, we expect people to learn these negotiation skills and to do something about it. For instance, they can use one of the lenses like this one, which is called the reality test. And it is based on the negotiation principle of educating the other people. Let reality be their teacher. The future reality of working with the deadline, and inspired by this lens, we can act in this situation by asking these people what they think will happen if we accept their unrealistic deadline. And you might be asking yourselves if this will work. And we actually asked for software practitioners to participate in a focus group where they were exposed to a pressure scenario. And our goal was to assess the perceived usefulness of the lenses. And we also collected data on their assertiveness profile and personality traits. And what we found was that they used many of the cards that we expected them to use in that scenario. They found it useful. And the person with the lowest assertiveness profile still felt uncomfortable with the situation. So we saw an improvement opportunity regarding this. But the person with the highest assertiveness profile said that the set of lenses actually helped him to gather arguments to defend the estimates. And what we're doing next, we're working on a digital simulation to combine it with the defense lenses and to further support these people in gaining negotiation skills for these kind of situations. And that's it. Thank you.
So thank you, Patricia. Very, very well on time of your 5 minutes, even if you had a little bit more. So let's go then right away to the next talk, which will be a presentation by Gunnar Kudryavets. I don't know if I've pronounced it correctly. The unexplored terrain.
It's cool.
Yeah, okay. I don't know. The unexplored terrain of compiler warnings. So thanks, Gunnar. Your turn.
Yeah, first of all, thank you everyone for attending this talk. My name is Gunnar Kudryavets. My co-authors are Aditya Kumar from Snap, Nachapal Magapan from Meta, and Ayushi Rastogi from University of Groningen. So ironically, I think one of our co-authors is currently either introducing bugs into compiler or fixing them, and second one is fixing compiler warnings. So today's talk is not about AI or ML or blockchain. It's about what we call in industry kind of unpleasantness of reality. So if we look at a typical development process, software evolves on a daily basis, engineers make changes, compiler toolsets get updated. Eventually, all of it results in compiler warnings. And then the question becomes, what do we do with those warnings? There is no consensus, approaches vary widely, and there's not enough evidence. So our entire study was kind of motivated by our experience in industry across various companies, Facebook, Microsoft, Snap, so on and so forth. The status quo is currently based on mainly anecdotal evidence. So pretty much engineers talking based on their personal experience, based on the projects they worked on. Teams in the same organization also tend to use very different approaches. So you can have a same product and one team will fix all the warnings, other team will ignore all the warnings. It will highly depend. And as a side result, we have a situation where there is lots of confusion. And if you ask engineers, like, what should we do with warnings? Like, depending on a person you ask, you may get very, very different answers. And purely kind of has anecdotal experience. The problem is present across each product, each team I have personally ever worked on. So now, what happens? One of the key observations we can make is that people have suffered in past. So for example, people have had enough experience with bugs, defects, and so on. They want to kind of try to fix the warnings as much as they can. Other people, also with a similar experience, tend to have an opposite viewpoint. They say, well, there's no evidence that warnings actually indicate real problems, so we don't fix them. Most of the guidance comes from gray literature. So there is only one study we found, Raymond Moser, 2007, where an observation is that the more warnings you have in your code, there's some sort of correlation between defects. But the study was on a very short and very small data set, so it's very hard to kind of make conclusions based on what is happening in industry. One of the main reasons engineers are not fixing compiler warnings is, like pointed out, no evidence. And second, there's a general distrust into the validity of warnings. So engineers look at it, if they have false positives, the usual tendency is just to start ignoring all the compiler warnings. Also, impact on engineer's career. So for example, as an engineer, you have to spend 1 week fixing 50 warnings, or you can spend that week working on features, performance bugs, fixing security bugs. You will choose working on something which has known value. Compiler warnings currently don't have it. And another thing why engineers do not fix compiler warnings is, general cost is very high. For example, if you integrate some part of legacy code, or you pretty much move your code into a larger code base, the potential effort may take weeks, months, or in some cases, even like we've seen periods where it takes like 6 months to clean up entire code base from the warnings. So now the question is, what can we do about it? Based on our kind of findings, what we can do is explore the current state, because our experience is mainly based on industry. We don't know much about what is going on with open source. Ideally, provide some sort of evidence about why fixing warnings is useful, and conduct case studies about projects that have zero tolerance policy towards warnings. Is there actually any benefit to it? So I think I'm going to end my presentation with kind of just a general call for help. There are many things as researchers everybody can focus on, but figuring out this topic, there's a clear impact on thousands of engineers who are like struggling with the same problem every day, every project I have ever worked on. So with that being said, thank you so much for your time. I'll be more than happy to take questions, debate, and if anybody wants to collaborate on this topic, I'll be more than happy to work with you. Thank you.
So thanks, Gunnar, for your presentation. Before the questions, we have the third and final presentation of this session, this time by Christoph Gotte. And the title is Big Data equals Big Insights, operationalizing Brooks Law in a massive GitHub dataset. Well, it's late here, so...
Sorry, it's a terrible word. I should have not have put it in the title.
Sorry. So, Christoph, your turn.
Thank you very much for this nice introduction. So indeed, we're trying to ask the question today, does big data automatically lead to big insights? And I'll try to tie this a bit to Patricia's talk in this session, because in the end, we're trying to operationalize Brooks Law in a massive GitHub data set, and that will hopefully give us some insights on how long a specific team size will actually take to complete a project, which will then feed into that data. So my name is Christoph Gotte. I'm a postdoc at the Chair of Systems Design at ETH Zurich, and I've listed my collaborators for this work on this slide. So let's start by recapping Brooks Law. I assume that everyone at ICSI is very familiar with this. Nevertheless, I thought it would be a good idea to write it down again here. So Brooks basically states that adding human resources to a late software project makes it later. What is not so known about Brooks Law, at least to many people, is actually the many different reasons that Brooks states in his book on why this is the case. And one of the key reasons that we're looking at in this paper and that literature has looked at in the past is a communication overhead, which grows exponentially, or at least superlinearly, with the amount of people that are in a team. And studying exactly this communication overhead, recent studies have found both an increase in individual productivity with team size, as well as a decrease in individual productivity with team size. And thus, the different studies using similar data and performing similar analyses actually yield contradicting results is something that I think should worry us, because we're doing quantitative studies. We also heard the keynote a couple of days ago, no, yesterday actually, that told us that quantitative research is very good and the numbers should be believed. Actually told us the opposite. But nevertheless, people tend to believe these numbers that they see. So the question we're trying to answer in this talk is there some middle ground between these prior results? Is there some sort of optimal team size where prior to this, the left-hand side holds, so there's an increase, and after that, there's a decrease? And if so, what causes these different contradicting conclusions? What causes these results that we see in the literature? In order to do this, we have looked at 4 challenges in the analysis of big data that we identified when looking at these papers. First is data quality. All papers that we considered looked at a large corpus of GitHub data, but which projects of this GitHub data set are actually suitable in order to study team collaboration? At the same time, we need to look at population validity. If we look at GitHub projects, we have a very small, very high skewness towards small projects. So most people work in teams of 2, 3, 4, 5 people, and then there are only few very large projects. So if we just take a random sample of GitHub projects, we'll likely get very small projects and not a very wide range of projects on GitHub, and that might bias our results. The same with the construction of our regression models later and the operationalization of our variables. So how do we operationalize productivity of teams of individuals, and how do we operationalize the size of an open source software development team like they are on GitHub? There are no lists that exist that we could use. And finally, we also looked at omitted variable bias. One variable that we identified in past papers that is a very important variable actually for the interaction between team size and productivity is the coordination between different team members. And overall, what we did is we developed a curated data set to study productivity in open source software teams, which we also make publicly available. We compared multiple different operationalizations for productivity and team size. And finally, we also controlled for the interaction structure in our models. Unfortunately, I don't have time here to go into detail on exactly how we did this. But instead, I want to jump to the results and actually tell you what we found in this talk. So there was one general overarching finding, which was a negative relationship, so proof for this Ringelmann effect that was talked about in prior literature, between productivity and team size. Particularly if we look at these regression models, we find that a doubling of a team size is typically associated with a reduction in individual productivity by 25%. I need to be very clear here, the overall productivities of these teams still grows by adding more people, but each person contributes less. So the overall productivity grows less than one would expect. If you look on the right-hand side, I show the initial regression models that were basically based on the regression models that also were run by these other papers. And we fit a linear and a quadratic model. And actually, we find that for this specific data set here, the quadratic model is the better fit. So there is some sort of evidence that there is an optimal team size even for these open source software projects. And in fact, if we look at these plots here, we can see that the optimal team size is somewhere between 10 and 20 team members. However, you can also see the big variance in this plot on the right-hand side, which tells you that there is a low explanatory power of our simple regression model for this specific data set. But we can significantly improve this by controlling for the interaction structure, as I already hinted at earlier. However, if we do so, the productivity increase that we just saw here with this quadratic term decreases. So now the question is, well, where does it go? Where does it decrease to? And this is basically the final slide where we want to look at, well, how did other papers, or what is a potential explanation for finding a positive relationship in such a data set? So if we look at the top right-hand figure, this shows the relationship between team size and productivity here in terms of number of lines of code for different levels of the mean in degree. What is the mean in degree? The mean in degree here is the amount of unique individuals that I edit code from, so that I collaborate with in my team. And as we can see here, the more people we collaborate with, the more productive my team is actually overall. And if you look on the bottom right-hand side, you can actually see that especially for small team sizes, the in degree goes up significantly with the increase in the team size. So if you're not careful and you're not controlling for the interaction structure, you might actually jump from one of these in degree lines to the next one. And in a special case of Simpson's paradox, actually find a positive relationship, particularly for small teams. If you couple that with a focus on small teams, which you obtain by either studying the entirety of GitHub, so mostly small teams, or random sampling from the entirety of GitHub, which also focuses you on small teams, you actually can get an erroneous positive relationship between team size and productivity, especially for this left-hand side, since you forgot about the right-hand side. So what did we learn today? Well, the first lesson is on big data, in my opinion. So we found that claims that we analyzed all of GitHub, for example, are not really helpful, because actually big data does not automatically lead to better insights in terms of what you're trying to study. Instead, there are a bunch of different challenges that you need to address and account for in order to get reliable results. Secondly, if we look at team productivity, well, we overall find a negative relationship for most of the team sizes. However, we also find evidence that adding members to very small teams can actually increase their productivity. However, the factor here is actually this in degree and the number of interaction partners rather than the larger team size in the first place. I hope this made you interested in looking at the full paper. I show here the QR code that you can just take that takes you directly to the paper. There's also a reproducibility package and the data set I promised earlier, which are available on Zenodo. And finally, 3 years ago at MSR, I published this package Git2Net, which I updated and maintained throughout this time, which you can now use yourself. We implemented all the productivity measures for ICSI, so you can use this package yourself and actually add additional projects onto this data set in case you want to run a similar analysis on different data or from different Git repositories. With this, I close. Thank you very much for your attention.
So thank you very much, Christoph. Thanks as well to Gunnar and Patricia. So these were the 3 presentations. So we have lots of time now for discussion. So you see the clapping hands here. That's the part we're missing with online presentations at the end. No, it just gives you a booster. So I see the audience like to know what they saw. So as you all know, it's now Q&A, so you have 2 different ways to make your questions. You can use the chat or you can open your mic. Both of them are okay. So I would first like to give the turn to our speakers if they have a question for the other papers, because we know I know you've been asked to read the other papers. I don't know if you want to go first. If not, I as a session chair can start a little bit of the discussion. But if anyone wants to go first, please go. Patricia says yes. Patricia, do you want to go first?
Okay, I can go.
Okay, fantastic.
I was just thinking of the presentation of Gunnar about the compiler warnings, and that was really interesting because, when I first saw your research, your results, I was connecting with something that we did in the past, and we investigated the reasons people in the software industry have for padding their estimates. And one of those reasons was for improving the overall quality of the product. So, for instance, they wouldn't find time in their schedules to fix bugs in production. So they would pad another task, unrelated task, just to get this time. And I mean, I think I was just thinking how if they don't fix the bug in production, they don't find time for that. How will they find time for compiler warnings? I mean, do you know what I say here?
Yeah, so usually they don't. So there are some exceptions. So I'll tell you the true story. I used to work for a long time on operating systems, and at some point I took like 2 days of vacation to fix some compiler warnings in some security-related code, which I thought should be fixed. And it's an absurd situation. You have to take your own vacation days to fix warnings. The root cause is very simple. So engineers are generally charged on the value they provide. So for example, let's assume I'll go and fix 50 warnings in some device driver. For me, the career benefit is like almost zero. If I'll go and spend that 3 days fixing a performance bug or fixing an existing known bug or some crashes, that's a good thing for me. So at some point, people will start making decisions based on what's good for them, not necessarily what's good for a product. And that's mainly kind of related to entry-level engineers. Senior engineers who don't need any more power or money, they can do whatever they want. But mostly, it comes down to the fact that in ideal world, yes, there's a benefit to fixing compiler warnings and product gets better. In reality, we make all decisions based on what's good for our career. And I know it may be very nihilistic answer from industry.
No, I was curious that you talked about the senior engineers. Do they have a behavior of fixing the compiler warnings?
Yeah. So here's the root reason. Yeah. So senior engineers usually tend to deal with debugging and fixing complex issues. And during that, they kind of root cause the problems. And for example, based on my experience after spending like years in kernel debugger, I can clearly see the causality between hard bugs and something which could have been prevented by fixing an integer overflow or function call or unsafe something. So I'm extremely motivated to fix those issues because I don't want to sleep like 4 hours under my desk while trying to trace down the bug if it can be fixed by 5 minutes of just writing some random C code.
I see. Thank you. I think that was it.
Okay, I'm going to ask you a question in return. So
Okay.
changing estimates. What's your theory? What motivates people in industry to change their estimates? Is it fear? Is it something else?
Yeah, sometimes you have an unexperienced developer, for instance, and they are interacting with a more senior developer or something. So they end up feeling that they are doing something wrong and they change their estimate. Just to give you one example, but sometimes it's clear-cut pressure. I mean, the manager wants that way and they simply yield. They don't try to understand the reasons behind that pressure, which is something that could help them. They don't try to think and discuss other options of commitments, because a commitment is establishing the scope and the deadline, this set of variables. I mean, they don't try to change, for instance, the scope, given that the deadline is fixed, for instance. So we expect that our artifacts help them to change this mindset of, well, there is something we can do. We can at least try. I mean, in this previous study, I saw people changing their estimates in estimation sessions. I saw that happening, It's not something that came from other studies only, or that I heard them talking about in interviews. They did.
Thank you.
How much of this behavior do you also think is attributed to the fact that the estimates were wrong in the first place? I just know from my own experience, when someone asks me, how long will you take to write this paper? I usually say something way too long because I'm very careful, or way too short because I don't see an obstacle ahead that I should have seen maybe.
Well, sometimes the estimates are wrong. I mean, sometimes, and sometimes we accept that. For instance, we understand more of the requirements, or someone talks about a smarter solution, which takes less time to implement. And that's okay, changing because of that. I am talking about harmful pressure, making commitments unrealistic. And people accepting this is a big problem, because they will not pay attention to compiler warnings. They won't have time for that. So I hope that it's not easy to separate the situations when someone is changing the estimate because it was clear he or she was clearly wrong or thought of some other thing. It's not related to pressure. To situations where there is pressure, it's not hard to separate, to be honest. I don't know how much, what's the proportion, but I believe it's a high proportion.
Yeah, I just assume that if there's pressure because I made a mistake in estimating my deadline, or if there's pressure because my boss thinks it should be done by this point, the negotiation will go quite differently because you have a different starting ground for the negotiation.
Once I heard a PO, a product owner, she didn't have a technical background, so she didn't know if the estimate was wrong, but she would apply pressure to estimators because she said, well, if I don't understand them and don't understand the estimate and the why of the estimate, why it takes so long, I will not be able to talk to the client and to defend the estimate to the client, I won't be able. So they have to convince me. So yeah, sometimes the pressure exists because of this.
Just one side comment purely from like industry. So software engineers have become kind of like lawyers. Our time is kind of accounted by hour. So this means engineers are very, very expensive. And so usually when you go and give an estimate and say something takes 2 weeks or 2 months or 3 months. So I've gotten to the point where I was asked to provide estimates into like 2 to 4 hour buckets. Because the question will be, why are we taking this engineer and asking him or her to work on this project for like 3 weeks? Why can't it be done in one? And you kind of end up spending like literally days just chunking everything down into those 4-hour pieces and just showing that, yes, that's how long it takes. That is kind of the unfortunate reality.
Gunnar, if we go back to the warnings, I know yours is a paper from the software engineering in practice track, but does this problem not stem from the education part? So I see how we teach at universities and how we manage warnings, and this is a warning, so don't care about it, or care less. I mean, even it would be nice to see in the books we use how warnings are treated and how warnings are presented, and maybe that's the root cause that is then taking over to industry. And you already have it's a warning. I have my deadlines, that's the other paper, and then it's a warning. That means it's secondary step, and then of course the excuse of the positive the false positives and so on, but maybe an excuse. But I think we already train our students so that warnings are second class problems.
I totally agree, because when people come to this and see the warnings, they're like, well, this is not real. It's not an error. Because, I mean, I only have anecdotal evidence of going and talking to maybe tens or if not hundreds of developers and asking them, okay, why didn't you fix this? And the answer is always the same. It was a warning. It's not real. It becomes real when people, for example, enable warnings as errors, or you have a very, very authoritarian policy that you must fix your warnings. If you commit code with warnings, you're a bad engineer, you're a bad person, and so on and so forth. That's the only way I've seen this being fixed. But yeah, otherwise it comes down to this is not real. It's just noise.
Okay, good. I would like to ask the audience if there are more questions. If not, as you see here, we have a vivid discussion. So we don't need actually many more people, but it would be nice if you contribute as well with your Q&A. So let's ask Christoph some things, so that gets as well some questions. So one of the things that many of us have looked at is the Linux kernel. And Linux is big and it's productive and so on. And the reason that has been always told to us is that it's because of its modularity. Yes. And one of its parts is modularity, and that's and then probably if somebody comes here from the area of software architecture, then they would say, yeah, that's why software architecture is that important. And I see in your metrics you have communication and so on, but you don't have modularity. What would you tell about this, especially those software architects?
So in terms of modularity, I think there is modularity in our data for the simple reason that we're looking at co-editing networks. So I look at whose code do I edit? And if I edit code of a lot of people, then I basically spread out throughout the entire project. Whereas if there is only very few people that I edit, then we have these small communities. I did not control for any code-based things here, for the simple reason, actually, that the study I'm doing is over 200 projects with different programming languages, and I did not find the tools that allowed me to have these different features for different languages in a reliable manner. What I did actually do is I tried to figure out if there's differences in scaling for different programming languages. But there was, maybe 200 projects were not sufficient in terms of data, even for 5 programming languages, despite this being a huge amount of data. But there was no pattern in this whatsoever. But this was also just curiosity. What I already said in an earlier session is actually, you shouldn't only think about optimizing productivity. I mean, this paper was clearly a response or a follow-up to these other papers that I found in the literature while trying to figure out what is actually productivity in these software development teams. And then everyone told me something different, and I wanted to figure out, well, how can I get the right answer in this case? And that was at least my aim. But in my PhD thesis, I actually looked at performance of software development teams rather than productivity. So I looked at all these different aspects as well that makes these teams productive. And in my opinion, I mean, you can say Brooks' law says that coordination is actually something negative because it makes you less productive. But actually, it enables the entire team as a whole to be more productive. So while there's a cost per individual, the entirety increases. And we've also found that the coordination patterns, so basically how we structure our team, has a significant impact on the productivity and essentially then also the performance of the team in the end. And that's what we controlled for it here. But if you have a very modular structure, I mean, we're collaborating with a software development company where we tested exactly this. If you have a very modular structure, and then the developer that was responsible for this module actually quits, then you have a huge issue because nobody can fill in the role of that person. Whereas if you have a non-modular structure where basically everyone, like an agile setup, that's what they refer to it here, where everyone at least knows part of the other people's work, then it's much easier to replace people once, as they call it, the truck hits or Google comes and basically just pays better. So I think that would be my answer to to the software structure.
Thank you. I have a follow-up question because if I look to the IT industry, the big companies, what I've heard, at least in Google, they have teams always, I would say small teams, which collaborate with other small teams. I'm always thinking about 4-5 programmers. I think last week we had a talk from people from Spotify, and they call it tribes or whatever, and they are also small teams, 4 teams, but they also try to have information flow to the other extent. So that's maybe it's different than in open source projects because you have a mix of volunteers and professional developers. I don't know now which sample you have taken, but I'm thinking, I mean, OpenStack is very industrial, but the typical GitHub project is probably not non-professional. So it would be nice to see if to take, like, let's say, more industrialized projects and to see if they behave different, which probably they have. So we have looked in the past how difficult it is to make a commit. And if you do heavy code review with a +2 and so on, then I think it was in a time span of 6 months. It was 12 commits in 6 months, so 2 commits per month, which is very low. But somebody from industry said, "Yeah, that's our productivity, around those numbers, not much more." And if you think about smaller projects which are lighter, then the productivity number of commits is higher, of course, but then maybe in lines of code and quality, I don't know, is different. So that it's a very tough question. So I think that we need more research on that. So
certainly, and I hope the tools that I've developed over the past years actually enable people to do this research. Because when I started, basically, I had to first develop a tool in order to get the data in the first place. Then I found out I wanted to do author disambiguation, and there was no tool that I could use, just some algorithms. So I developed an author disambiguation tool, and now we're actually at the point where we can collect this data in some sort of efficient manner and actually run the analyses on that. For this project, there was a big variety of industrial or more industrialized and less industrialized projects. And my interpretation of why the number here with 10 to 20 is larger than these tribes or the family pizza idea that you have with the team size, in my opinion, is because you have this heterogeneity in contributors, which we controlled for with an activity variable in the end. So, but nevertheless, the idea about team size, at least how it's also pointed out by the reviewers correctly, is the idea that everyone who contributes to an open source project is in the end a member of the team. But nevertheless, there are members who have 1,000 commits or 1,000 lines of code written, and then there are others that did 1. And I think because of this heterogeneity, you have a larger number that is still sustainable and where you can still increase the productivity even of the individual.
Yeah, thank you. So we still have time for further questions. I don't know if anybody in the audience, we've got the chat, or you can open your mic.
There's a question in the chat.
Yeah, I see right now, right? There, in this sense, do we have the same problem with microservices?
Oh, yeah. I see lots. I see. I didn't scroll down. I was there. Okay. Fantastic. So, let me see. So, where should I start? I should have scrolled down. It doesn't do it automatically. Sorry about that. So, I see lots of questions, so I don't know now where to start. So, I see one from Christoph first. So, I go just order. So, so from Christoph, I don't know if he already has addressed this. No, my experience when writing papers is that no matter what you do, things will always happen in the final days before the submission deadline. We all know about that, no? So there seems also to be a positive aspect of a mismatch between estimate and target. On the other hand, if you have too little time, you will likely have the quality issues that Serad you mentioned. How does your framework go about balancing these facets?
Yeah, I try to answer it in the chat, but in any case, we have research results suggesting that a little bit of pressure is okay, in the sense that people will raise their productivity when they feel a little bit of pressure. But it's up only to a certain point. After that point, it starts affecting the quality of product and life quality of people as well. So we actually tried. I gave you one example of the lenses, but we actually have a set of lenses to try to make people change their mindsets, as I said, and including to deal with these harmful pressure situations, and to try to separate the situations where there's not much we can do about. There is a lens which is called choose your battles, right? Because you're not going to be able to avoid pressure completely in all situations. Sometimes it can be in the interest of the estimator to accept a deadline that's not so realistic, for instance. It depends a lot on the situation. I'm trying to win a contract, for instance, and that's going to make a big difference for my company. It's better for me probably to accept that and go on, and to compensate for that later on. So we try to address this on our set of lenses too, because when you look to the original negotiation methods, they're talking about this. They are talking about think more about the situation, think clearly about it. Maybe the other person is actually proposing something that's better. I think I don't know if I got the answer.
Well, there are more questions for you, Patricia. So I go it in chronological order in the chat. So Ayushi asks you if you foresee a role of power play in addition to the personality traits that you've presented in the negotiations.
Yes. When we were studying the negotiation methods, we were worried about this because, estimators are usually software developers and testers and, the more technical people in the team, and they are leading with people with a business background sometimes, and people usually in higher positions. So in a sense, they are in a less powerful position, And we looked for methods that consider that would give these people in positions of less power a possibility to negotiate, because in fact, when you look into these methods and remembering the definition I gave you, it's kind of a communication, a conversation. You have to engage in this conversation to understand the other side, to see what's good for them, and that fits on what's good for you too, and to think of alternatives, of commitments that can, address your interests and their interests too, right? And it's not, sometimes we are people with the technical knowledge about what's actually possible to do. You know better in this point most of the time. Of course, sometimes we are dealing with managers and tech leads that know a lot about the technical part too, but I assume everybody's on the same side, right? Software teams and the clients and the managers, and everyone is on the same side. So although there are differences in power, we are trying to achieve the same things. And I hope and we expect our lenses to help people navigate these situations, you know, to provide them with these means, because we don't learn these skills in our universities and colleges when we are undergrad students. Nobody is teaching, as far as I am a lecturer actually in a university in Brazil, so I know what I'm talking about. We don't teach our students this, but I think we need that.
Thank you, Patricia. So there is a follow-up question by Ayushi, which is you have already responded in the chat that it's not clear. Maybe if Ayushi clarifies that, we could talk about it later on. I'm gonna move to one question for Gunnar for Gunnar from Christoph. So, and Christoph says many tools I work with on a daily basis, LaTeX and Python, do not actively show warnings to me as a user. Would this be a place to start working on awareness?
So I'll first say that I'm extremely biased when it comes to warnings, because I believe that, we should have zero tolerance policy and we should treat each piece of software like it's, a rocket ship going to Mars. But in my opinion, yes, because I think it will provide a good framework for people to understand that, hey, look, there are warnings, they are useful, and maybe it kind of translates into other parts of life, like as an engineer or scientist or whatnot. So I fully support this idea.
Well, the point is, sometimes if a warning is important enough, then they include it in the compiler. That's what we get sometimes as user. No, I'm thinking, especially in Python, you get Pylint, and then you use Pylint, and there are many things from Pylint from older versions that are now part of the interpreter, and then you don't get them as warning anymore. And because that's tolerance zero. I mean, then why having warnings? Include them in the compiler. Should we do that?
It's usually the default settings that I use, it just runs through, and as soon as there are no errors, for example, with PyTest, it will tell you warnings if there is an error, but it will not show you warnings if it runs through, in my experience. And it's the same with Python. I'm not going to fix all my underfull H boxes that you get in every single document that you have ever compiled. So I don't really get the zero tolerance policy there, but also that LaTeX and not code. So maybe that's the blind spot here.
I think my overall philosophical comment will be that life is a harsh teacher. The moment you're going to have a first problem, it will take days or weeks, and sometimes even like memory corruptions may take like months to debug. And you figure out it's caused by this one little line of code, which could have been fixed because if somebody would have looked at that, W extra warnings or whatnot. That's where it kind of sinks in. At least that was kind of my experience, because I used to ignore everything. It's like it's not real. And suddenly kind of life comes and makes its own corrections.
So the thing is to be on the active side of what we can do as engineers. So when I think about the warning system, I'm thinking about the C compiler and all the flags and so on. That's extremely complex. And then it wouldn't be a first step to have it easier, in the sense that you can make the compiler be more strict or less strict, and actually or 0.5 strict or things like that. I know this is difficult, but yeah, it's probably better than the current situation. I don't know what you think, if that's a good idea, because it's part of, we're talking about socio-technical issues more than technical issues, because the warnings are there. And how to move a big community of developers towards having a better attitude towards warnings is a difficult task. So something has to be done. What should be done?
I tend to agree. I think usability is part of the problem, because if you look at kind of your average compiler, like C, C++, there's like 200, 300 different types of warnings. And what people generally do, first they run with a default setting, and if they feel slightly better about everything, they maybe do W all, W extra, W pedantic, W everything, and then comes more confusion. One is subset of another, some warnings overlap, some warnings only recommended to be run by the compiler developers. So yes, I think the current usability story is not ideal. And yeah, ideally what you would want is something very, very simple. It's like default, a little bit more, little bit more, little bit more, without having to look at the compiler diagnostic page for days at the end and figuring out what does this warning do under this language standard, under this operating system. Agreed, usability is the key.
And then a final question, then I go to Christoph, because there's another one in the chat. Do you think that projects that use code review are better in this regard than projects that don't use code review? I mean, reviewers, do they look at these warnings, or do you think that's something they are not aware of, and they look at other things? They well, clarity and whatever, but not at compiler warnings.
So it depends on a reviewer, and it depends on the motivation. Like in industry, so I don't know, lots of people will disagree with me, but unless we're talking about low-level systems code, kernel, file system, device drivers, the trend in industry has been currently speed over correctness. So let it sink in for a moment. It's better to ship something which kind of works as fast as possible, instead of just spending months or years fixing every known bug. So this means that during the code review, if the question is that, okay, can we commit this change in 2 hours and push it to production in 2 days, versus will take 3 days and fix all the compiler warnings, make sure everything is 100% correct. Usually, it's a very pragmatic decision. Yes, let's assume 5% of scenarios will fail in production. That's an acceptable trade-off. So speed over correctness.
Yeah, fair enough. Good answer. So I have to move to Christoph, because there's some, here Tayana asked specifically about microservices and and modularity, I guess. Yeah.
Clarified, yes. I'm not too familiar with microservices, but from looking at the architecture, from thinking about it, I would see the same problem there. But the paper I presented today was about productivity, not about modularity, and not about resilience in the essence of these software development communities. I hope that paper will come in the next year, maybe next year at ICSI, who knows, and then we can have a deeper discussion about it once it's published. And if you want a preprint of it, you can always contact me, because it's already written up in my thesis, so it's all there. But the general idea for me would be that there is some sort of trade-off between productivity and resilience. As soon as we have these microservices, in the sense, they're very good if we want to take a part out of them. So in that sense, they're very productive. And if one person can work on each aspect, that's also very good. However, as soon as that person leaves, and we have seen many cases, many open source projects where central developers left the project at some point in time. And as soon as that developer takes a bunch of knowledge out of the project, so if you had a truck factor of 1 essentially beforehand for this specific aspect, you get a big problem. And I would see the same problem potentially occurring in microservices. Yes.
Thank you, Christoph. Yeah, Ayushi, just open your mic and.
I have a follow-up question for Patricia. I was amazed by the idea of negotiation. The way I see negotiation, it's more of an art, and not just a list of bullet items that you tell people and they are eventually voila, just able to solve the problem. So what do you think? Like, I'm trying to understand, how can you make this information available to developers such that they can make some valuable changes in their process? Is it like going to be a tool? Is it going to be a set of guidelines? And how do you make sure that it's accessible to the common developer?
Okay, now I think I get it. Well, we are devising an artifact in the form of lenses. The idea of the lenses come from the human-computer interaction community, with people working with gamification, with games, actually. They have design lenses where you, instead of describing things as guidelines, you describe in the format of questions, to make people think about it. And we started with this idea, but, and we wrote it. We designed the lenses as we showed in the slides, but we also wrote a booklet explaining the lenses, giving examples. And during the focus group, people was like, okay, the booklet is short, but I don't know if people are going to read it, and how things are. So we are now working on defining a digital simulation in the form of interactive videos. And in these videos, people are presented to pressure scenarios, and we created these scenarios from situations that we saw in previous studies, and that also came from the literature in software engineering. And in these scenarios, we present the lenses, and we also talk about how you can use the ideas of the lenses to deal with the situation, And this was the manner we found to actually show the negotiation principles adapted to this estimation context. And it's a hard thing to do, because you're trying to teach people principles, but they have to develop this skill, and we're struggling with this situation right now.
And maybe just a follow-up and an alternate way of thinking, would it make sense to present the needs of different stakeholders to the other party? So for instance, if there is a management, can you make available the requirements for an engineer and vice versa? Would that be a way?
Yeah, there is one of the lenses, we call it the pressuring forces. What's behind the pressure? Why are they asking for a reduction in your estimate, or to change the deadline, or why are they trying to impose the deadline? So instead of presenting the software developers or anyone estimating, presenting specific situations, within the lenses, we actually ask them questions to think about this, to think about what's behind, the pressure. And with the digital simulation, we give examples, we discuss more in this line of, well, you can do that in this situation. And I don't know if I answered you.
Thank you.
And if you have any other ideas, we can talk a lot about this.
So thank you, Ayushi. Thank you, Patricia, for the answer. We still have 2 more minutes to go. So there is time for a final question or a final comment. I don't know if any of the presenters wants to say something.
I think I'll make a general comment. I think for me, it's been a very pleasant discussion. So thank you, everybody who asked questions. Thank you, everybody kind of being open and kind of making me feel involved. So it was worth of my time.
Yeah, it was
I
really
felt exactly the same.
Absolutely.
Yeah, it was really a nice discussion, and it's a pity that we are not on site, and now with a coffee break we could keep on talking and chatting about this. That's the things I miss from virtual conferences. Yeah, you have your coffee. I have my bottle of water here, but it's not the same. So then we're gonna close this session on software economics. I would again like to thank the 3 presenters for the insightful presentations and papers. And I hope you enjoy the virtual ICSI. And if you are lucky enough to be next week in the on-site one, then enjoy as well ICSI there, face to face. And that's it on my side. I hope you have a nice rest of the day. Good morning, good afternoon, good evening, wherever you're located. I hope to see you soon. Bye-bye.
Bye.
Ciao.